Okay, so today I thought we would just do a very, I don't know, light introduction to Bayesian statistics, okay? And we'll just talk about this kind of from this high level. I mean, we'll get into some math here, okay? Don't get me wrong, but just kind of from a high level, like what is all of this about? And I don't know, your key ideas here. As far as, so, I don't know, I think people hype up the feud between Bayesians and frequentists. I think everyone's a little bit of both. Maybe not everyone. Some people might be very strictly one way or another. But I think there's definitely a lot of openness for both. Okay, so all of your classical statistics generally is frequentist, okay? And so if we think of frequentist statistics, okay, what is the definition of probability under frequentist statistics? Kind of your classical, like when you guys took intro stats at some point in your life, what did we say was the definition of probability? What does it mean for when we say the coin will land heads with probability 0.5? What does that mean?
It means that if you have like a giant pool of coin flips, or you flip it a bunch of times, the average will approach 0.5.
Right.
It's this set value of 0.5.
Yes. So there's this notion of in the long run relative frequency will approach 0.5, and that probability that it will land heads is some fixed value that maybe we don't know right yet, but it's a fixed value, right? And so what do I have here? It says our model may specify that we believe our data comes from a particular distribution with some unknown parameter values, and our goal is to estimate these unknown parameter values based on the sample in our data. In classical frequentist statistics, we often estimate these things via maximum likelihood estimation. And if you have some set of numeric data, your maximum likelihood estimate is going to be y bar, et cetera, okay? And if you have categorical data that, like coin flips, that go 0 and 1, your maximum likelihood estimation based on the sample will be the sample proportion p hat, right? And again, the notion here is that there is some fixed value that remains a mystery to us. We cannot directly observe it, but it exists, okay? And so this doesn't actually have marbles in it, but I've got this pouch, and the idea here is, I don't know, maybe we could count, we can feel what's inside the bag, and we can count that there's 10 marbles in the bag, okay? I use this to carry my microphone in it, but just pretend that you've felt around and you say, okay, there's 10 marbles in here, and we want to estimate, what proportion of marbles in the bag are red, okay? And so the easiest thing would be to just open the bag and dump it out and go, oh, okay, 5 are red and 5 are blue. It's 50% red, or 3 are red and 7 are blue. It's 30% red, okay? But we're going to pretend that we can't open up the bag. We just know that there's 10 of them in there, and some of them might be red. So we're going to draw with replacement. We look at one marble, we put it back. We look at another marble, we put it back, et cetera, and and so if we've done 10 draws with replacement, let's say we got the following, okay? R, B, 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 R, whatever, okay? Which is 4 red and 6 blue, all right? And we say, what can we say about the proportion of red marbles in the pouch, okay? So our sample is 40% red, okay? And that's going to turn out to be the maximum likelihood estimate. So did I already talk about maximum likelihood estimation in this class or not yet? No. Do you guys, some of you probably remember maximum likelihood estimation, and maybe some of you have forgotten. So the idea here is we just write down, we assume some kind of model for generating our data, and that model has some kind of probability distribution, okay? And we take that and we apply it to the data we have to get our likelihood equation, right? So if we're just assuming this is some, like a Bernoulli trial bag, right? Every time I reach in the bag, there's some probability P of getting a red marble, right? So, so the probability of getting red would be P, and then the probability of getting not red is 1 minus P, okay? And so in my data, I saw red, blue, 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 red, blue, red, red, blue, blue, okay? And so each time I see a red, it's going to be P. Each time I see a blue, it's 1 minus P. And this exact sequence ends up having the likelihood of P raised to the 4th, because I saw a red marble 4 times, and 1 minus P, the probability of not a red or a blue marble, 1 minus P, that happens 6 times. Okay, so the total likelihood of this exact sequence is P to the 4, 1 minus P to the 6. Okay, if I didn't have this as an exact sequence and I said any sequence of 4 reds and 6 blues qualified, because just at the end of the day I saw 4 reds and 6 blues, the thing would be very similar, but we would just throw in a constant in the front, the kind of the binomial constant, and that would be like 10 choose 4. We would throw that in the front, which represents basically all the different like arrangements you could have. Like you could have all 4 red in the front and 6 blue in the back, or you can have, red, red, blue, blue, blue. There's going to be 10 choose 4 possible ways to arrange these things, okay? And you just throw in a constant there. But overall, this probability is P to the 4, 1 minus P to the 6. Is that okay? So this is the likelihood of getting this sequence of data based on the marbles that appear in my bag, right? Or that we have observed. And so maximum likelihood estimation says, let's pick the value of P so that this thing ends up being as big as possible. We want to maximize the likelihood of the data that we got, right? So this is the data. Basically, the fact that we observed our data, like kind of the notion is that we don't want to think that some unlikely event happened to us, but that our data is kind of the most likely outcome of whatever's in the bag. So we want to find what value of P will make this thing as large as possible, okay? And so, there's a few ways you could do this. One is like, this is a variable of 1 parameter, so you could just like graph it, right? You can take, P can be any value between 0 and 1, and so you can just plot all the values between 0 and 1, or like, maybe not all of them, but you can do like 1,000 of these things, right? And you can plot them, and you can see, all right, which values of P are most likely and stuff like that. The analytic thing would be to maximize this using calculus, right? So you can take the derivative of this and set it equal to 0 and solve for P, right? So the only problem with taking the derivative of this directly is that this is 1 minus P raised to the 6, and so you would have to kind of expand out to that polynomial thing, and you've got like, I don't know, 13 terms in there or something. So it's going to be, you don't want to mess with that. So one thing that we often do is we deal with the log of the likelihood, the log likelihood, all right? And the log basically turns products into sums, right? Which is useful because pretty much if you have independent observations, the total likelihood of all of those independent observations is a product. Okay, that's what the kind of the independent assumption is. And so, it's going to turn that product into a sum, and that just makes our life easier. And the value that maximizes the log likelihood is going to be the same value that maximizes the original likelihood, because the log function is what we call monotonic, so that, if there's any 2 values, A and B, if A is bigger than B, then the log of A is always going to be the log of bigger than the log of B. So if you have some value that maximizes this thing, the same value will maximize the log of that thing. Okay. So anyway, we do this, we take the log, okay, so the log of this becomes 4 log p and 6 log 1 minus p, right? Then you take the derivative of this, and the derivative of the log is 1 over that thing, right? So now you get 4 over p, and you get 6 divided by 1 minus p, and chain rule the negative p, so now you have a minus, and then you set that equal to 0, and you solve for p, and so you get 4 over p is equal to 6 over 1 minus p, and then you multiply both sides by 1 minus p, and you get 4 minus 4p equals 6p. Now you get 10p is equal to 4, and p is equal to 0.4. And this is going to be the value of p that maximizes our likelihood, okay? Do we feel okay with that? All right. Okay, and then so someone might say, all right, so here's the thing, right? Here's our bag. There's some proportion of red marbles in here. We've drawn 10 marbles out and go, okay, 4 of them were red, 10 were not, so we think there's 40% red. And now we ask, okay, what's the probability that the next marble I draw is red, okay? And then we would say, all right, that's going to be 0.4, right? Because 40% of these things are red, we're going to say it's 0.4, right? All right, and then I could even ask, what's the probability of drawing 1 red and 2 blue if I draw 3 marbles with the replacement, right? So now I'm going to do a binomial thing. I'm going to draw 3 marbles with replacement. And I say, what's the probability of getting 1 red and 2 blue? And so this is going to be 3 choose 1. The red, probability of red is 0.4. That has to happen 1 time. The probability of blue is 0.6, and that has to happen 2 times. And that overall probability ends up being 0.432. Okay. All right, and that's the frequentist approach. And I don't know, do we have any objections? Does anything feel off about the frequentist approach? Okay, and and some of you are like, no, and others are like, yep, definitely there's a problem here. Okay, so the biggest issue here is, right, is that we've only seen 10 observations, and based on our 10 observations, I'm ready to just say, okay, my bag is 40% red, right? I plugged it into maximum likelihood. Maximum likelihood is 40% red is 40% red, okay? And that feels a little bit like maybe we're putting too much stake into a single value of 40%, right? Because it is, yes, it's true that 40% probability is the best guess given the 10 observations that we have, but 10 observations, that's not a lot of observations, right? And so with classical statistics, what we try to do is we say, okay, you know, here's this thing called standard error, right? And we say, we get an estimate of the standard deviation of the sampling distribution. And we say, all right, you know, you got a small sample, you've got a big standard error. You have a big sample, your standard error is a lot smaller, right? Okay, but the interpretation of the standard error, the confidence interval, is a little bit hard. I don't know. So if your standard error, I mean, if your confidence interval goes from 0.1 to 0.7, right? So if the confidence interval for the proportion that is red in the bag is 0.1 to 0.7, what is the proper interpretation of that? You'd say, I am 95% confident that the proportion in the bag is between 0.1 and 0.7, right? Are you ever allowed to say there's a 95% probability that the bag, proportion of the bag is between 0.1 and 0.7? Like, part of us maybe wants to say that, but maybe your stats teacher said, like, you're not allowed to say it. So you know, like, okay, I'm not allowed to say this. Or, you know, for example, we could do make a confidence interval for, I don't know, the mean height of the population, right? So we could say, you know, we sampled a lot of people, and I'm 95% confident that the average height of an adult male is between 5'9" and 5'10" or something like that. Okay, we can say something like that. Does it? But your stats teacher might have said you are not allowed to say there's a 95% probability that mu, the average height of everyone in the population, is between 5'9" and 5'10". Right? So maybe I'll just write this very quickly. All right, so 95% confidence interval for mean height of adult men in the USA. All right, and then we'll just say this goes from 69 inches to 70 inches. Okay, all right. So okay is I am 95% confident that the mean height of all adult males in the US is between 69 and 70 inches. Okay, I'm just making these numbers up, by the way, so don't quote me on this. Okay, but not okay is there is a 95% probability that the mean height of all adult males in the US is between 69 and 70. All right. All right, so what's the difference between confidence and probability here, right? Because that seems to be the only difference between these statements. And by the way, this is frequentist, okay? If we are frequentist. This is the modifier right there. Okay. So the frequentists said what? This is okay, but this is not okay. All right. So why? I know you know, but all right. Here's my or I don't know. Any takers on this? Yes. Okay. So here's my my illustration here. All right. So I have a coin here. Right. I didn't do this right already. Okay. All right. So here's a coin, and I say, what is the probability this coin will land heads?
50%.
All right. 50%. 0.5. We're all in agreement there. That is correct. Okay. All right. So now I flip. Oh dear. All right. Let me do this again. All right. My life is so hard. Okay. All right. I have flipped the coin successfully now. Okay. And now I ask, what is the probability that the coin has landed heads? Okay.
Yeah, it's...
All right. So now some of you say 50%, and others are like, I'm not so sure. And then I'll do one more thing. I have looked at it, and I cover it back up, and I ask, what is the probability that the coin has landed heads?
You tell us.
And so now you're just weirded out. So from a frequentist perspective, the last two questions were nonsense questions. The coin has landed, and it either landed heads or it landed tails. You don't know how it landed, but it is nonsense to ask what is the probability that it has landed heads, because it either did or it didn't, right? Probability for a frequentist only exists for things that are uncertain, okay? Before we flip the coin, we can say, what's the probability that it will land heads? But once the coin has landed, even if we haven't seen it, once the coin has landed, it is nonsense to ask what's the probability that this thing that is a fact or not, is a thing, right? And so for a frequentist, the mean of the population is a fixed value, okay? There's no uncertainty about it, okay? That's the frequentist thing. So So with the coin, you can say, I am 50% confident that it has landed heads. Okay, you can say that. That's a fair statement. But it is wrong to say there's a 50% probability that it has landed heads. Okay. So, so that's why it is, so we can say I'm 95% confident that the mean of all heights is between this and this. Okay, but for a frequentist, it is wrong to say there's a 95% probability that the mean height is between here and here. Yeah, because it either is between here and here or it's not, right? Either the coin landed heads or it didn't. So there's no probability. It's just, you know, we can say there's we're 95% confident that it's between here and here, but we can't talk about a probability. That's the frequentist view. Okay. So, you know, for a coin flip, it landed tails, by the way. For a coin flip, I don't think it makes sense to really try to be Bayesian about, like, these questions, like, don't quite apply. But I think for the Bayesian, okay, I think it makes sense for talking about the mean height of the adult population. We can kind of treat the mean height of the population as a random value, okay? So as far as the frequentist thing, this probability that we're between here and here, that's kind of the notion that, like, maybe I could, like, freeze time and go out and measure every single human adult male in the US, measure their height. I gather up, like, I don't know, 150 million values or something, and then I take the average and I get some number, okay? That's kind of the, like, the frequentist. For that, you to find the true mean height, you'd have to do something like that, okay? For the Bayesian, we might say that, you know, at any moment in time, the value, the mean height in the population, that like fluctuates, right? Like people, I don't know, however we define adult, right? Like some people have their 18th birthday and now they are considered an adult male in the US. Some people enter this population and then some people die and are no longer part of the population. So there's like random things that influence the mean thing. And so we can't, you know, the idea of freezing time maybe appeals to the frequentist, but you know, that's not really possible. And so the Bayesian says the mean itself, the mean of the population itself is a random variable. Okay? So the whatever parameter we're looking at itself is a random variable. And if it's a random variable, then that means it has a probability distribution, right? So because it's a random variable, it has a probability distribution, okay? Which means certain values are going to be more likely and other values are going to be less likely. And then we can start talking about probabilities. We can say that, you know, for our random variable, 95% of the time, or like there's a 95% probability that this random variable, the mean, is between 69 and 70. We can say that, right? So we are allowed to say there is a 95% probability that this random variable, that is the mean, is between 69 and 70 inches. All right, and so this is kind of the shift that we have. Now, when you're Bayesian, okay, the fact that it's a random variable and it has a probability distribution, it really makes the math more complicated, okay? You've got a lot more sums and integrals to deal with, all right? So that's what we'll look at today, okay? We'll just kind of look at like kind of these very basic probability questions, but from a Bayesian perspective, where we, you know, now have to deal with sums and integrals, okay? But is this all right? Just kind of the switch from saying there's a fixed value, okay, versus there's a probability distribution for this thing. Right? Yeah.
So isn't kind of the difference between confidence and probability that, like, if you have so like confidence would be there's a 95% chance that we get this data given that the population value is between 69 and 70. But Bayesian would be there's a 95% chance that the mean value in the population is between 69 and 70.
Yeah, okay, so let me, so the confidence interval, that 95% confidence comes from the notion that says a random sample drawn from, so this is frequentist, a random sample drawn from the population will produce a confidence interval that correctly captures the mean 95% of the time. So like, it's the 95% of random samples will produce a confidence interval that's correct, okay? And so our confidence interval went from 69 to 70, therefore I'm 95% confident that the population mean is between these values. So like if you did like 100 confidence intervals, like meaning you drew 100 different random samples and you produced a 95% confidence interval for each of those 100 samples, we would expect around 95 of those resulting confidence intervals, each one different because each random sample is different. We would expect about 95% of those to correctly capture the population mean and about 5% of them to be wrong, okay? And you don't know which one you have, and you just kind of have to bank on the fact that 95% of them are right, so you're 95% confident that that yours is one that is correct, but you could easily be wrong. I'm trying to think if we're allowed to say I'm 95% confident and use these actual numbers themselves. And I want to say it's just that the process of making a confidence interval is correct 95% of the time, and therefore the one that we have, we can be 95% confident about it, if that's okay. All right. Okay, so this is what I said. Okay, so we're going to treat, so this is kind of the key idea. The Bayesian statistics treats the parameters of the population as a random variable. All right, so first I'm going to start with kind of a discrete case, all right? Just, I don't know, because the math is a little easier in terms of dealing with a sum rather than an integral, but then it's also like super tedious because now like I have like 11 of these things to add every single time. So I'm going to say before I even open the bag, right, the fact that like I counted, like I felt around and I said, okay, there's 10 marbles in the bag means that the proportion that's red can either be like 0% red, 10% red, 20% red, like, because there's 10 marbles, right? So up to 90% red or 10 out of 10 are red, okay? And before I open the bag, I have no reason, like right now I don't have any reasoning to say that one particular proportion is more likely than another, right? Before I even like draw a thing. So I'm gonna just say all of these values between 0 and 1, 0, 0.1, 0.2, 0.3 are equally likely. And so we have 11 values that are possible, and they're all equally likely. So each one gets a probability of 1 over 11, okay? We call this our prior beliefs, or the prior distribution. This is the distribution that we think applies to this value p. P being the proportion that is red in the bag. We're going to say the prior beliefs, or the prior distribution of P, and it's unfortunate, I probably should have used a different letter here, but the prior distribution of P is going to be 1 over 11 for all 11 of these values here, okay? So we'll say this is a uniform prior. Okay, and then we go through and we update, we observe data. All right, and we see we get 4 red marbles and 6 blue marbles. What did I write? Okay, And so we do this, and just, and this is just kind of like descriptive words, no math yet, okay? So we say, all right, we got 4 red, 6 that are not red, 6 blue or whatever, okay? And so, maximum likelihood estimation says the most probable value of P is 0.4, okay? But the fact that we only saw 10, like, if someone says, I think the bag is actually 50% red, you'd say, yeah, I guess that's a reasonable thing to think about, okay? Because we got 4 out of 10 to be red, but that could have easily happened even if the bag were 50% red, okay? And then someone says, well, no, I think it could be 30% red. And you go, yeah, I guess that's also possible, right? Maybe I just, in my random sampling, I got 4, right? And, but, if somebody says the bag is 80% red, we'd go, well, I guess that's technically possible. It seems less likely, but it's not impossible either, right? And so we would reflect, we would kind of update our thing, right? We would say 0% red is impossible. The fact that we saw red means 0 is impossible, right? And the fact that we saw some blue means 100% red is impossible as well, okay? And, 90% red seems very, very, very unlikely, okay? And so anyway, that's what this thing does. Now, I will describe how we got these numbers later, okay? Or I'll explain how we got these numbers, but this is what we would see. This is our updated distribution here, okay? And we would say 40% is most likely after seeing this, 50%, 30% are also likely, 60 and 20% are possible. 10% is fairly unlikely, 80% is really unlikely, 90% is also very, very unlikely, okay? But I guess we're not ready to say impossible, okay? But 100% and 0%, those are impossible, okay? And so this distribution, this is known as what we call the posterior distribution. This represents what we believe to be the proportion that is red in the bag after we have observed the data, okay? Now, in the case of the bag, I don't know, maybe frequentist makes a little bit more sense because there's always the argument that you can unzip the bag and dump it out and count, right? And that it would be a fixed value, that what's inside is not necessarily a random variable, right? So there's always a little bit of a philosophical thing, like is the thing inside here a random variable or not? I don't know, right? But in a lot of cases, I think it is reasonable to treat the unknown thing as a random variable and treat your probabilities as kind of like what you believe that random variable to be, okay? And so you'll often, if you read anything about Bayesian statistics, they always talk about probabilities as a belief and stuff. Oh, I guess before I go on, I'll come immediately back. This is a very good book, Doing Bayesian Data Analysis, and you can download it for free because you are a UCLA student and you pay into our library subscriptions, and so you get this excellent book with dogs on the cover by John Krushke, all right? So this is a really good book. I highly recommend it. It's written in a very accessible way. I think this professor is actually a professor of psychology, and it's good. And if you try to buy the hardcover, it's a lot more pricey. So anyway, okay. So just make sure you download this while you're here tonight. All right, or connect via the VPN, right? Okay. That's like the VPN is so great. Okay. All right. So so once we have this thing, okay, then that is our posterior distribution. Then the way we answer our questions is now completely different. Okay. So before with frequentist statistics, we just took our maximum likelihood estimate. There was just one value, 0.4, and we just plugged that in and we said, all right, what's the probability that the next one's red? That's going to be 0.4. What's the probability I get 1 red and 2 blue out of 3 draws? And I just plug in 0.4 and I do the problem here, okay? But with Bayesian stuff, okay, now I have to actually consider there are technically 9 possible values P could be, all right? Some of them are more likely, right? 0.4 is more likely than 0.8 and 0.1 and 0.9, okay? But others are also likely, like 0.3 and 0.5. So what we're gonna do is every question we answer has to be weighted by its probability. So the question, just this simple question, what's the probability that the next marble I draw is red, now becomes a weighted sum. I have to say, well, it could be, P could be 0.1, okay, but it's 0.1 with only probability 0.0123. It could be 0.2, but it's only going to be 0.2 with probability 10%. It could be 0.3, and that's a likely value with around 22%. 0.4 is the most likely value of around 0.2759. 0.5 is quite likely with probability 0.22. And I go through and I do all 9 values, each one weighted differently, and then the total kind of weighted sum is around 41%, okay? 0.4167. So it's not drastically different from the maximum likelihood estimate, but it is different. And the way we got this is not just to take the tallest value and say this is it, okay? We consider all the possible values and we weight them accordingly, all right? Is that all right? Doing this weighted sum for the probability of just getting P. Okay, so that's just taking all of these values from this thing, right? And then the question of what is the probability of drawing 1 red and 2 blue in any order if I draw 3 marbles, it used to just be 3 choose 1, 0.4 to the 1, and 1 minus 0.4 or 0.6 to the 2, okay? But now I take that thing and I multiply it by P, okay, the probability of each value. So I have to do 3 choose 1, 0.1 raised to the 1, 1 minus 0.1 squared, and I multiply it by the probability that is 0.1, which is 0.0123. Then I try it for 0.2, and I multiply it by that probability of 0.09, and I do it for all 11 values, but I mean the 0 and the 1 are zeros, so we throw those away, right? And I do this for all of them, and I finally get to 3 choose 1, 0.9 to the 1, 1 minus 0.9 squared times 0.002, okay? So you can see this, the amount of computations grow quite a bit, right? So, and this is just the discrete case, okay? But, and so when you do this and you calculate it, you get 0.3846, and that is considerably different from what we had, I don't know how considerable you'd say considerable, but with the frequentist thing, we said 3 choose 1, 0.4 to the 1. This has a probability of 0.432, and now we're getting something different of around 0.3846. Okay, so the question's quite different, right? And so in general, okay, whatever question, the probability question you have, we'll call that function h of p or h of theta, okay? So this is some question that depends on the unknown parameter, in our case p, or in general theta, all right? So if we say, what's the probability of getting 1 red out of 3 draws if the probability of red is p, you can plug in any value here and you'll get a slightly different number, okay? And in terms of getting the value, it's going to be the product of that function h of theta multiplied by the probability distribution of theta, p of theta. Okay, so you multiply those two and then you sum this up. Right? Okay, so that's what we have for this. Before I go on to the continuous case, I just want to make sure. I know there's a lot of math going on here, but well, I I don't know, maybe I'm out of touch, but I'm trying to keep the math like simple and digestible at this point. And is this okay? All right. Okay. So what do we do if it's continuous? So right now I said P can only be 0 or 0.1 or 0.2 or 0.3, but let's say you don't know how many marbles are in the bag, right? And then so technically there are infinitely many values. I guess technically it would be just the continuous, the rational numbers, but anyway, it's beside the point. So technically there's an infinitely many values, right? Like P, like if there was like some weird number, P could be like 0.11573, or it could be 0.34289, or right? It's not necessarily going to be these nice 0.1, 0.2, 0.3, right? So now you have this continuous distribution for P, okay? And so P of theta is going to be a continuous distribution, and H or P of P, I guess, the probability distribution on that proportion P is continuous, but the H itself will still be this, right? 3, choose 1, whatever P you plug in, okay? So, how would you do this? Well, instead of the sum, now you do an integral, okay? And I don't know about you, but I struggle with integrals, okay? Like, I can do like integrals of polynomials and like basic sine functions, but beyond that, like if you tell me to like integrate by parts, I'm going to be like, oh gosh, what is this? U, V, D, 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 it's like, oh, like it's hard. And I end up, it's so bad, I just go, all right, let's go to Wolfram Alpha, type it in, and see what it spits out, right? And I'm hoping the Wolfram team can tell me what the integral is. Otherwise, I'm in trouble. So integrals are hard, and so Bayesian statistics can become quite difficult if you get stuck with some integral that you don't know how to integrate, right? Next week, we'll look at some strategies for getting a good estimate even when you have an integral that you can't deal with, okay? And that's going to be the Monte Carlo methods and, all of that stuff, okay? But for now, we're going to just say, all right, we're going to do integrals for all of those kinds of stuff, okay? All right, so let's go back and talk about how did I get these numbers, right? Like, I just told you, I said, all right, we're going to get these numbers, and this is how the numbers that we get, right? So how did I get these numbers, okay? So that's, we're going to cover that here using Bayes' rule, right? Okay, so this is why we call it Bayesian statistics, is because we use Bayes' rule. And Bayes, I don't know my statistics history well enough, but I believe Thomas Bayes, I don't know, do you guys know the story? Or I don't know, maybe somebody knows better than I do. He was a monk, I believe, and he was trying to do some math to kind of make an argument towards the existence of God, and so he wrote this thing about like the probability of the evidence, or the probability of this based on the evidence, which is what we have here, A given B, is going to be, what's the probability of, and he didn't even say it, but he, in these exact terms, but this notion is much attributed to him. And he's from like the 1600s or something, like super long ago, but now we use this for everything, okay? All right, and so this was, I don't know how much of your probability rules we need to cover, but we've got the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. Are we okay with this probability notation, or do we need to take a moment to review? Okay. Nobody said anything. I got a thumbs up from the front, but all right. So okay. Well, good. All right. And so when we apply this to our data, okay, we're basically what we want is we've got some unknown parameter. Okay, for our bag of red marbles. That unknown parameter is p, the proportion of red, okay? But in general, we just use the unknown parameter, we'll call that theta, okay? So that could be like the mean of the population or the proportion that's red in the bag or some other parameter value, we call that theta. And then we say, we wanna know, okay, what is the distribution of theta? What is this distribution of the unknown parameter? What values of the unknown parameter are more likely? What values are less likely based on the data we've observed, which is y, okay? And the way we do this is we just say, all right, this is going to be the probability of y given theta times the probability of theta divided by the probability of y, okay? Did I break this down? Okay, I broke it down here, okay, which maybe you can look at that page. But so y given theta, this is what we call the likelihood, all right? We're going to say this probability of y given theta is if we know that the proportion p is some value, what is the probability of getting this sequence of data that we have observed, okay? Or if we know that the mean of the population is this value, what is the probability, or what's the likelihood of getting the data that we have observed, okay? So, so that's what this is, okay? Probability of theta is what is the prior distribution of that parameter. So before you even opened up the bag, before you looked at any of the data, did you have a notion or an idea that certain values are more likely than other values, right? So are you able to kind of express something there, right? Like if like some of the values some values of this unknown parameter might be more likely than others, right? So maybe you don't know how many marbles are in the bag, but maybe you saw them put in one red marble and one blue marble, okay? So maybe right off the bat, you can eliminate the probability that it's 0% red or 100% red, right? So you might be able to state that somewhere in your prior distribution, okay? So before you even look at the data, you might be able to eliminate the chance that red is 0 or blue is, or red is 100%, okay? You know, if we're talking about the mean height of all adults or something, you might say, well, I know for sure that the average height is not under 5 feet and the average height's not over, 6 feet or something like that. There's different things you can specify, okay? This bottom, okay, this P of y, this is known as the marginal probability. It's the probability of y, the probability of getting this data, all right, regardless of these values theta, right? So basically, I observed 4 red and 6 blue. What's the probability I would get 4 red and 6 blue if theta was 0.1 or if theta was 0.2? I have to, if I consider all of the possibilities, what's just the probability of getting 4 red and 6 blue, regardless of the value of theta, okay? This thing, P of y, does not depend, there's no theta in there, right? There's no theta value in here. And so this thing, the posterior distribution, is a function of theta, whereas this has no value of theta. So this is a constant with respect to theta, okay? Which is convenient for us, okay? Because that's gonna, at least for the Markov chain stuff, Monte Carlo stuff, that's gonna be important. Conveniently for us, it is the sum or the integral of all possible values of the numerator, okay? And really this purpose, this value in the bottom, it serves one purpose, and that is to make sure that when we sum all of the values across all possible values of theta, or integrate across all possible values of theta, its purpose is to make sure we get a PDF or PMF, which means the total probability of everything has to add up to 1, right? So, that's kind of the rule of any probability distribution, is that if you integrate the whole thing, the area is 1, or if you have a probability mass function and you add up all the probabilities, it adds up to 1, okay? This thing is just a constant to just make sure that everything adds up to 1 or integrates to 1, okay? All right, so I think I've kind of summarized those up in that text there. Okay, so we'll take a look at the discrete case here, okay? And we'll look at how did we get these actual values, and we'll do the computations for this. So I have this, okay? This our prior distribution. Before we looked at any of the data, somehow we know that there's 10 marbles in the pouch, okay? And therefore, the probabilities, the values that P can take on are anything from 0 to 1, and we're going to just say all of these are equally likely, and we're going to just put 1 over 1/11th for all of these things, okay? If before I opened the pouch I know that there was 1 red and 1 blue, then I would just put 0 for the first one and 0 for the last one, and everything else would be 1 over 9, right? Okay, and that would change my answers, right? So, so depending on what you knew prior to observing your data will affect what you have going on here. Okay, so this we are going to ask, what is the likelihood of the data? This is, what is the likelihood that I get 4 red and 6 blue marbles, okay, given some value of P, okay? So my Y, my data is 4 red and 6 blue, given some proportion P, right? And so this is going to be P to the 4, 1 minus P to the 6. If you wanted to, you can also throw in the binomial constant 10 choose 4 in the front, okay? And that would just adjust everything by a constant, okay? And in the end, at the end of the day, it makes no difference because that constant will get canceled out later, right? Okay, so we're going to just say, all right, if P was 0, what's the likelihood? And that would be 0 to the 4, 1 to the 6, so that's gets a likelihood of 0, right? If P was 0.1, what's the probability of getting 4 red and 6 blue? It's 0.1 to the 4, 0.9 to the 6. That's this number with a bunch of zeros. 0.2 to the 4 times 0.8 to the 6 gives us this. If P was, and we can see, if P was 0.3, my number is 0.00095. And if P was 0.4, then my number is 0.00119, okay? And P.5 is 0.0097. So we can see that the values around 0.4 and 0.5 and 0.3 have higher likelihoods, which makes sense, right? Which just kind of makes intuitive sense. And so this is what my table looks like. This is the likelihoods, right? And R makes this easy. You can just do 1 through 9 over 0.10. So P is all these values over 10. And then you can just say, well, let's do P to the 4 times 1 minus P to the 6. And we get all of these values here. All right. When you look at likelihoods, likelihoods are not a probability function. So these are all small, and if I added them up, I would not get a sum of 1, okay? And that it feels weird, right? Because this looks like a probability thing, but it's not going to add to 1, all right? Because likelihoods are not subject to the same rules as probability distributions. They both derive from the same thing. This adds up to 1 if we, no, this in of itself does not add up to 1, okay? This is just a product of likelihoods, all right? The PMF is really just the P and the 1 minus P, all right? And this is a product of 10 Bernoulli probabilities. So we're not going to get something that adds up to 1, okay? All right, and so the numerator, the numerator is the product of the likelihood and the prior, okay? So basically, I'm going to just take all of these numbers that I computed here, and I'm going to multiply all of them by 1/11th, okay? And that just makes all of our numbers really small, even smaller, okay? It's fine, all right? So if I take the prior 1/11th, which is a constant for all of them, I multiply my likelihood times the prior, and this is what I get, okay? That's going to be my numerator. And so these are all the different values I get. All right. So very small numbers. All right, and then so the marginal is the probability of y, which, to make things easy for us, is just the sum of all the numerator values. All right, so here I have 11 numerator values, okay, and the marginal is just there, so that it's just basically to scale the numerator values so that the result will add up to 1. Okay, that's the purpose of this marginal probability. So we're going to just take the sum of the numerators. The numerator is the likelihood times the prior, and that gives me a marginal value, and this is a constant. And so the posterior distribution is going to be the result of the likelihood times the prior divided by the marginal. And so that's what I have. Okay, so I'm going to go ahead and do this. And I do this, and this kind of just shifts everything up to be just scales everything up. And so that when I sum all of the posterior values, they sum up to 1. And I can plot this, and this is the resulting posterior distribution. And these are the values that I used on that table. So if you flip to the 4th page, these values, I guess I rounded them off to 4 decimal places. Those are these values. 0.001227 rounds off to 0.0123, 0.0968, 8 is 0.0969, and so on and so forth. And so these are the values. If you round them off to 4 decimal places, gives you the posterior distribution that appears on page 4. All right. Is that okay regarding how I got these values? This is it's the likelihood times the prior divided by the marginal. Where did I use my Bayes rule? Where did that go? It's this, okay? It's just y given theta, that's the likelihood times the prior, okay? In our case was 1/11, the constant for everybody, divided by the marginal. Okay. And so this gives me this. This is my posterior distribution. After observing 10 marbles where 4 of them are red, this reflects my current beliefs about the distribution here. Okay. What if I say, all right, well, I've only observed 10 observations. I should gather more data, right? So you go and you decide, let's gather more data, right? Okay. So what we can do is we don't have to throw away what we learned from before, right? So far I've seen 10 observations. 4 of them were red, and after that I said, okay, based on what I've observed, this reflects what I believe the proportion red to be. 0.4 is the most likely value. 0.3 and 0.5 are still quite likely. You know, the other values are not impossible. Other values between 0.1 and 0.9 are not impossible, but quite unlikely, considering that I saw 4 red and 6 blue. Okay. All right. So what do I do if, so I'm going to gather more data, and this time I gathered more and I got 6 red and 4 blue, okay? So in total I've seen a total of 10 red and 10 blue, okay? But as far as this observation goes, this set of observations, I have 6 red and 4 blue, okay? So my likelihood is p to the 6, 1 minus p to the 4. Is that okay? All right, so for the new batch of data, my likelihood is p to the 6, 1 minus p to the 4, okay? We're going to go through the process, right? So this is my old posterior distribution, okay? 0.0 whatever, right? This is the vector I have representing my posterior distribution. And so for this set, now this is going to serve as the prior distribution for kind of my second, right? So I'm going to say, all right, I'm going to take what I learned from before, and now I'm starting off with this knowledge, okay? So I'm going to keep looking at this, and before I look at my new set of data, right now my current beliefs is that 40% is the most likely value. 30 and 50% are also likely, and that's what I have before I look at the new batch of data, right? So I'm going to take the old information that I learned, posterior, and I'm going to set that to be my new prior distribution. Okay, and now I'm going to calculate the likelihood for all of these possible values. We're going to say any value between 0 and 1 are possible, all right? And let's just calculate the likelihood of getting the data we have. So I'm going to p to the 6, 1 minus p to the 4, because that's what I've observed. I observed 6 red and 4 blue. And so I do these calculations, all right? The marginal is going to be the sum of all the numerators, the likelihoods times the priors. Okay, so I didn't even bother printing that out. That's just going to be some constant value. And again, its purpose is so that the result adds up to 1. Okay, and so the resulting posterior distribution is going to be the likelihood times the prior divided by the marginal. And these are the resulting numbers, okay? These are the resulting numbers. I guess before you even look at, I mean, they're on your paper there, but if prior to looking at the data, 0.4 was the most likely value, and then when we looked at the data, we got 6 red and 4 blue, what do you think the result will be, right? So prior we thought 40% was most likely. We looked at the data, we got 6 red and 4 blue. So maximum likelihood estimation in this case would say 60% is most likely, right? So what would happen when we kind of combine the two? My prior beliefs, where I got 40% was most likely, and now my current set of data, which says 60% is most likely, what do you think is going to end up happening?
50%.
50% is going to be most likely, right? Like that, I think that makes intuitive sense. And if we look at the data, indeed, that's what we get. Okay, when we look at the posterior distribution after combining my prior beliefs and my new set of data, which is reflected in that likelihood, and I combine the two, we get 50% is more likely. 60 and 40% also have a high probability, okay? And then the other numbers are very unlikely to be the case. The neat thing is that whether we treated it as a single experiment or if we broke it apart into here was my first 10 and I got this posterior distribution, here's my second 10 and I combined that, okay? Or if I just treated it and said, let's look at, here's our total data. We have 20 observations, 10 are red and 10 are blue, because I could have also done that. Okay, if I did it that way, I would get the exact same results, okay? So which I think also is reassuring to us, right? That I don't have to worry that I did something wrong by, if the data comes streaming in and I wanted to say okay, I got the first 10 observations. Let's go ahead and do an analysis here, okay? And we get this number, and then more data streams in later, and I say, okay, let's update our thing. I don't have to worry about saying okay, do I take the results of my first thing and then update, or do I have to clear everything out and just say okay, now I have 20 total and stuff like that. So because if I did this as 20 total, okay, my prior distribution is 1 over 11 for everybody, okay? And then we're going to say my likelihood is going to be p to the 10, because I got 10 red total, and 1 minus p to the 10, 10 blue total. And And if I do this, my likelihood is all of these numbers, and then my marginal is the sum of the numerator values. Likelihood times the prior divided by the marginal, I end up getting the same values, right? So if we look at 0.5, it's 0.3700141587, which is the same thing I got here, 0.370014, right? So if I did all 20 observations all at the same time, I get the same resulting distribution there, okay? And that's good, right? Okay. Do we have questions on this? Yes.
So the chart, the histogram chart, when it's centered at 0.4 and the other one is 0.5, I mean the highest.
They're not. It's not symmetric. Yeah.
But how come 0.5 is more symmetric than the 0.4?
Yeah. Well,
Isn't that the thing?
no, it's
Can we just think about it as sort of like one pooled observation where we pull 20 marbles and have 10 red and 10 blue?
Yeah, you can treat it that way, or you can. Okay, so here, let me go back to your question, right? So your question here is, when we observed 10 observations, right, and we got 4 red, 6 blue, right? So we said 40% is most likely, okay? 30% and 50% are also possible, okay? But it's not symmetric, right? So we say, well, you know, it feels weird. You'd think like 50% is only 10% more than 40 and 30% is only 10% less than 40. So, you know, it's actually a little bit more of a coincidence that these are kind of symmetric, because there's no guarantee that things are going to be symmetric. So if you take it to the extreme, right? If let's say I got 1 red, okay? 1 red and 9 blue, okay? And I go 10% up, I would say, is it possible that it's 20%? You know, 10% is going to be the most likely value. Is it possible that it's 20%? Yeah, it's possible, less likely, right? Is it possible that it's 0%? No, it's not, okay? Because 0 is now completely impossible, right? So that distribution is certainly not symmetric. It's going to be, you know, the highest value is going to be 0.1, but it's going to be very skewed in one direction, right? And so what happens, and we can plot all of these different likelihood things, is that if you look at the kind of continuous distribution, or not the, I guess the continuous likelihood, is that so, all right, so I'm going to just do a sequence from 0 to 1 by equals 0. So I'm going to do this by 1,000ths, and then I'll call my likelihood to be, so we'll do p to the 4 times 1 minus p to the 6. All right, so we'll do that. And then let's just go ahead and plot p versus the likelihood, and we'll just do type equals L, and color we'll just do blue. Okay. Let's make this bigger. Okay. So so what we have is this, and if I let me just load this up here, is that these are not going to be symmetric. If I bring this to like 10% and 90%, okay, we can see this is E equals 0.1. So here's 10%, and let me just kind of add a vertical line at 0.2, and obviously the value at 0 is 0, right? So we can see this is certainly not symmetric. If I just shifted this to 2 and 8, okay, 20, and now I do 0.3, okay, we can also see it's not symmetric around this, right? And it's only when I get to 5 and 5 Okay, then it's symmetric. Okay, so as we kind of roll this from across the thing, it becomes symmetric here, but towards the end it gets more skewed, and so it's there's nothing that says this should be symmetric here. Okay, yeah, it's a that's what we've got. So as you move towards the ends of 0 and 1, which become impossible, it's going to force the distribution to become skewed. Okay. Other questions here? Yeah.
When we are doing it in two sets, like sampling once for 10 and then again for 10.
Yeah.
So we are basically sampling with replacement always.
Yes. So yeah, the whole premise here is, yeah, we're sampling with replacement, and so we can treat each thing as a Bernoulli, which keeps the probabilities of p and 1 minus p as constants, right? If we were sampling without replacement, and we treat this as a finite sample, not like an infinite thing, then everything we draw is dependent on the previous draws, right? So the first one has a probability of p, and then the next one has a hypergeometric distribution, and you would need to know the population, or the full size, and how many you've observed so far, and how many and things are of the hot or the success values and stuff like that. So yeah, just to keep everything simple, I've treated everything as a Bernoulli with independent with replacement, right? So and we can say it's without replacement if we have an infinitely large sample or something like that, or that our population is infinitely large, or at least large enough where drawing without replacement has negligible effect on the p's. Okay, why don't we take a short break here? We'll come back and we'll look at continuous case ones with, I don't know, I guess with some integral stuff. It's not too bad, not too bad. We're doing Bayesian.